Hello, welcome to Numerical Ship and Offshore Hydrodynamics. Today is the lecture 43. Today we are going to discuss about the Frank close-speed method. In last class, we stopped somewhere. We are going to start from that point. Okay, and this is the keyword that we are going to use to get this lecture. Okay. Now, if you remember, in the previous class, we said that we are going to use this Green's function to calculate the added mass and the damping, right. Now, here if you see that the complex part involves in this expression, which is the regular part. And of course, I do not say that it is not complex, but somehow if you take g equal to 1 upon r, it is a strong singularity, and if you take g is equal to ln r, it is little bit, it is not that strong, the singularity is a weak singularity. Now, but however, still it is difficult, and we have to deal with this also, and how to deal with ln r, etcetera, etcetera. At least for 1 upon r we have discussed, but major difficulty involves in this calculation of this particular term, okay, and we call this as a regular term. However, this is important because otherwise if you drop this term, then we have to discretize the free surface and things become little bit more complex in terms of meshing, the computational effort, etcetera. It will. So, it is better to use this Green's function, so that the domain of discretization becomes only the body, right. And this is the setup that we are going to use, that, and this is my section, and this section actually I add with number of state line, and we said that if you use the number of state line, then if it is a straight line, it is easier to find out what is the normal component. It is analytical and it is trivial also. So, now here this is the unknown sigma, that also we discussed. We first find out sigma, and then you have to put this sigma into the source integral equation to get the value for the phi. Now, here you can see that this is principal value that we are going to actually solve, because it is in complex domain, it has some cos component, sin component, and this is how actually you are going to get this value for this particular thing. Now, here if you see, this is why it is complex, because it is has a improper integral 0 to infinity, and in order to get this you have two series, which is C r theta and S r theta. Now, you see that C r theta and S r theta is given by this expression, and of course, this theta, the argument is given by this expression. However, this theta, theoretically it seems that this finding out this theta is very easy. I have this panel, I have this the straight line, and then if I do this, so this is my theta. So, it is easy. However, if you do this coding in reality, then you have to face so much of trouble because of this angle. We are coming here. Before that, it is very interesting in even this. Suppose I find out somehow the theta, then how I compute this term. Okay. So, now computing this term also it is very interesting to see. Why? Because if you look at this expression, it is summation this n is equal to 1 to infinity. So, it is an infinite sum, and it is r to the power n by, let us say, cos of n theta divided by n into factorial n. Now, we do not have any say on cos n theta, because this cos n theta is always oscillate between 0 and 1. So, it means that I have to multiply a factor which is between 0 to 1 with the other term. So, if I look at it, that let us say f of n, it is nothing but n equal to 1 to infinity r to the power n divided by n into factorial n, right. Now, so thing is that we need to multiply some factor between 0 to 1 with this. Now, think of this r, I mean this expression. Now, n is going to infinity. Now, you see, like if I try to plot this graph, okay. So, first let me erase this, and now let us try to plot this graph, which is like f n, let me write again, it is r to the power n divided by n into factorial n. Now, this one let us try to draw the graph. What would be the graph for this? Now, you have to take some the value for r. Now, let us take this length is this normally the L is the length of the vessel. Now, suppose you have here now, okay, sorry, is beam, in this case it is beam, and now this is, let us say this is the body. Now, at this point, suppose you have one point over here, and let us say you have this another point over here, and this is the difference is r. Now, you see, for instance, let us take some large value r equal to 10, let us say some realistic large value 10. Now, try to find out this value. Now, when n equal to 1, then this value is 1, it is 1. So, now I just plot f n versus n. Now, when n equal to 1, this whole value is 1. When n equal to 2, then it is, oh sorry, 10, sorry, the value is 10, sorry, very sorry. Now, when n equal to 2, the value is 100 divided by 2 into factorial 2. So, it is 100 divided by 4. So, it is 25. Now, when n equal to 3, so it is 10 cube, which is 1000, and divided by n into factorial n, which is 3 into factorial 3, which is 6. So, essentially it is 1000 by 18. If you take 20, then it is 50. Now, you can see that more than 50, some let us say 55, let us say. So, the point is that if you look at it, this series and this series has an infinite sum. Now, it appears that this value starting from 10 and slowly progressing like this way, right. Now, if I add this graph at infinitely, because you see this sum is infinity. So, definitely it's our what I said, like assumptions, it is blow up, because it will going to blow up, because it turns out to be a divergent series. Interestingly, it is not. After some point, you can see initially this r to the power n is increases much faster compared to n into factorial n up to some limit, some n t. Now, when n is greater than n t, after that n into factorial n is growing much faster compared to r to the power n. So, therefore, the actual graph somehow it will blow up initially, and then it comes down, and sometimes asymptotically it goes to 0. That is the nature of this thing, but you need to find out that what would be the convergent limit. Now, think of a computational thing, and how we can using the integer, use integer 32 or whatever, it has a limit. Now, if you keep doing this n into factorial n, like suppose if you write a very simple type of code, like it is you can take that, let us say f of n is equal to f of n minus 1 plus r to the power n divided by n into factorial n, right, and multiply by the sin n theta, and then you give a check if mod of f of n minus f of n minus 1 until it is less than epsilon, you have to again you just n is equal to n plus 1 and again you just do this operation. Now, this is how one should write a simple way, but if you do that you are going to get an error. Why? Because you do not know the limit of n. Now, in some situation, let us take m 30, let us try to. So, now if you try to find out f 30, it is nothing but f 29 plus r to the power 30 divided by 30 into factorial 30. Now, I have very much doubt if 30 into factorial 30 will return you integer value or not, right. So, once you start writing this code, this kind of things you have to deal with. Now, here I am not going to tell you that what would be the best logical way to approach to find out this solution. Okay. So, you think and then you take this as your assignment problem, some assignment, and come up with some logic. Okay. If you fail, then definitely we can discuss the same. Okay. Now, here what is the advantage? This is a very versatile approach, the Frank-Close-Speed. It does not depend on the shape of the sections, or even you can take the bulbous bow also, right. And then that disadvantage is definitely it is more complicated. If you compute the very accurately you try to find out what is the added mass, all these things, then radiation potential in fact in a way it is much more complex, because in other approach is really easy, because the solution is developed, we are having the chart, we have used that chart to get this. And also as you know, similarly like this 3-dimensional panel method code also, there also we have the problem of a irregular frequency. In some frequency that solution becomes approach to infinity, right. So, here also this is possibility. So, that is also you have to understand that okay, this result is not feasible, this is unrealistic solution. So, you must have some kind of idea about the irregular frequency. Okay. So, now I just listed upon some advantage and disadvantage of the conformal mapping methods and the Frank-Close-Speed method. So, it is a smooth solutions over all frequency range, the conformal mapping. So, we do not have any irregular frequencies there. Now, sharp corners, but its sharp corners are not you cannot get very, like if you take a rectangular barge exactly, right, and this is the section, it is very difficult to get using this conformal mapping. And also sections with very low sectional area coefficient may not be well represented. That means, this beta n, like if it is less than 0.5, so maybe the results are not that good. Okay. So, and also you really cannot map this bulbous bow sections, those things are not possible. And now, on the other hand, we have the Frank-Close-Speed method. So, it is does not depend on that what is your the cross sections, you can apply everywhere. Even you can use this the sharp corner also, you can use this for the Frank-Low-Speed method. However, we have the problem of the corners, sorry, the irregular frequencies. Some frequencies this solution may have blow up, getting some numerical instability, etc. Okay. Now, this is a classical the graph. It is now here. This is taken from a paper by Nuno Fonseca. I am in reference, definitely we are going to say this. Now, here you can see that in the Frank-Low-Speed method we can have this irregular frequency. However, in a conformal mapping we do not have anything, right. Okay. So, this is the problem. Now, now it is only one frequency blow up and remaining. So, it has more advantage because you can take any type of cross sections. Now, the main advantage of the conformal mapping is it is easy to apply nowadays, because theory is developed already and we know exactly what to do, right. So, it is now depending on the choice of who is coding to use this Frank-Low-Speed or conformal mapping. Okay. Now, and again this is the disadvantage, as I said, that in case of a even if you try with the very is Lewis curve fitting can go up to this, and if you really use many terms, like as you know that you can use only 2 terms for the Frank-Low-Speed method. If you take more than 2 terms and all, still you do not get the sharp corner. Now, also however, if you take any kind of shape in Frank-Low-Speed, this, all are possible. Okay. Now, you can see that here you can see that it is this shape is very critical, because you see that abruptly the direction of normal is changing, right. So, it might have some coding complexity, but it is possible, and this is not possible for Frank-Low. I mean, this is not possible for your conformal mapping techniques or Lewis curves. This is not possible, and this is of course possible for both. Okay. And now, this is the problem, main problem, as we mentioned before also. If you look at my previous slide, somewhere I mentioned that this involves angle of computation, that is not very straightforward. Now, you see what is happening over here. This angle, you can see if this is the source point and this is your angle. Now, this angle might lie in either from minus pi by 2 to pi by 2, or it is in minus pi to plus pi, or it is 0 to pi. All three are possibility. Now, if you really do not understand and carefully address this, the range where it is, then because the tan theta, if you remember, we have a tan theta. So, here all positive, then here this sine positive, cos negative, right here, and this is direction the cos positive and tan sine negative, and here both sine cos both are negative. So, eventually tan is positive. Now, in which range actually, whether it is from here, whether the range is here or whether the range is here, that is very much important to calculate exactly the value of this. Okay. It is only when you start coding using Frank-Low-Speed method, you can only realize at that particular point. Now, here for instance, I am just giving the 2 point here, right. So, x1 and x2. So, now here is straightforward, this is the theta, it is now you know that it is in which angle it is. So, it is theta 2 minus theta 1, right, because here if it is tan theta 2 minus tan theta 1. So, this is your theta. So, this theta is from this axis, it is, or this axis theta 2 minus theta 1. Now, suppose this is not this situation. Now, here it is here. Now, here this is the section. Now, here is the point. So, now what about this theta? Still theta 2 minus theta 1, or in this case it should be theta 2 plus theta 1. Now, it is depending on how you are measuring. Are you getting my point? Like if this is your here point and this is it. So, this theta, now I know this theta is nothing but my theta 2 minus theta 1, fine. Now, suppose your section is like this way. Now, tell me here it should be, if I do again theta 2 minus theta 1, I do not get it, because suppose this is my axis. So, it is your theta 2, and if you take the same orientation. So, this is your theta 1. So, then if you take in a same reference, then theta 2 minus theta 1 will not give you this angle. However, if you take this section, which is minus pi by 2 to plus pi by 2, whatever, in this region, if you take this way, then you can take it is theta 2 minus theta 1. Are you getting? Okay, let me explain again. Now, I take two situations. Here this is your source point and the cross section is, let us say, this is your cross section. So, I am lying here in this panel, which is it is 0 to pi in this region. So, then this angle is theta 2, this angle is theta 1. So, your theta is this theta is nothing but theta 2 minus theta 1. This is the picture number 1, absolutely fine. Now, what I am doing in the second situation. So, let us take the same point over here. Now, this section is here like this, and then this is your theta. Right. Now, if I try to go over here, so this is my as you know, it is my theta 2, and if I go this way, it is my theta 1. Now, my question is, can this theta 2 minus theta 1 gives you this angle in 0 to pi in this reference frame? No, right. However, if you take this reference frame and you define this as minus pi by 2 it is pi by 2 to minus pi by 2. Let us take this reference frame. Now, you see, now I change my reference frame. Okay, so let me do this. Erase. Now, in this second location, now what I am doing is, I am not doing in this reference frame, which is 0 to pi. I am doing it from minus pi by 2 to pi by 2. Now, this is my point and this is your axis. So, this is my the theta. Now, if I measure from here, so this becomes my theta 2 and this becomes my theta 1. Now, if I measure, I am always doing theta 2 minus theta 1, but now instead of 0 to pi, I am changing, it is from minus pi by 2 to pi by 2. The moment I change is this again now valid. See, this is how you have to set the thing. That is what, like if you blindly always do theta 2 minus theta 1, and if you always taking the limit 0 to 0 to pi, this is your thing. So, you really do not get the correct answer, is a possibility, right. So, therefore, one has to be very much careful on all this aspect. Okay. And this is the, so once you do this, once you find out this theta, and if you try to figure out that what is the algorithm, to get this value of C r theta and S r theta, then you can able to efficiently you can find out the value of the PV this complicated term, and then you are done with your Frank-Low speed method. Okay. So, now I am just going to finish this by showing some kind of result. This is all we have discussed. So, we are not going to discuss anymore. Now, we are talking about the coupling. As I mentioned that most of the time we are using that roll is uncoupled. However, in reality roll is really not uncoupled. It is always coupled with the sway. Now, how you see, like if you consider that this is your rolling, right. So, if this is the rolling, then it can be rolled like this way, or it could be roll as opposite way, this way and this way, right. Just see, it can roll this way or it can roll this way. So, now here this one should use the coupling between sway and roll. Okay. So, now that is what just the last part I just going to show you, this one, that the red one is the coupled one and then blue one is I just use the single degrees of freedom roll motion. Now, you can see that in this here that there is a difference, right. So, that is the one key point. People normally think that roll should not be is a single degree of freedom motion, but it is not. Definitely, if you want to solve the roll, you have to again use the coupled equation of motion with the sway. If you try to find out the heap, it should be coupled with the pitch definitely, and if you try to figure out the roll, it should be coupled with the sway, right. Okay. And again this is another picture, so like another I mean this coupled and uncoupled. Okay. So, with that and of course, this is for the different speed, right. As a summary, that at present the two dimensional strip theory are routinely used by the industry. Reason is very simple, because this added mass damping, all these things actually you can use using some kind of chart that is coming from the Lewis curve, and also we can simplify the exciting force also. We mentioned that using the buoyancy, that extra buoyancy, or in fact in case of a head waves we can figure out that using that simple added mass damping can represent the diffraction force. So, in many ways most of the industrial people, they are having this strip theory. Okay. And also there are many version of strip theories is available based on several theories. Here in this class we mostly focus on the two approach. One is by STF paper and second one is the June's lecture, not lecture, like the report. Okay. So, this is all for the strip theory. So, now before we finish this strip theory part, I would like to give you a small assignment that you can try in your home to write a strip theory code with lot of simplified assumptions. So, what are the assumptions? As follows. So, number one, you can take that beta is equal to 180 degree. Okay. The moment you take this beta equal to 180 degree, then you can write your this f d in terms of some added mass, some A33. Now you see that okay. So, second point is that you are only the heap. So, it is single degrees of freedom only the heap. Okay. So, then in that case FD3 you can figure out in terms of A33 and B33. Then how you get this A33 and B33? You can get it through some kind of chart, right. So, this chart maybe I will try to prepare this chart and give to all the students, so that you can get it. So, the A33, B33 you get from the chart, and then this Fruit-Cale law force, Fk force, it is analytical. So, you know how to do that. And then after doing all this thing, and then this you figure out how to get this C33, which is nothing but rho g into AWP, right, and you also know how to get the water plane area, right, if you know this the y values. So, you can discretize it, right, you can discretize it and you can take the area. So, you can get the water plane area. So, you get all these 3 terms, right, and also we have this data, what is the mass, right. So, therefore, after that use this strip theory that for that what we discussed throughout. So, if you get the sectional added mass from the chart, so how to get the, by integrating how to get the added mass for the body, that also you know, and then you solve this equation m plus a into x double dot plus b into x dot plus c into x is equal to your F exciting force, which is nothing but addition of diffraction force plus addition of Fruit-Kildler force. So, everything you can do it time domain, it will be easy for you, because you know the added mass in real number, you know the damping is a real number, you know C is a real number. So, then you need to find out the amplitude of FD using this analytical method that we have discussed. Not analytical, like that diffraction force in terms of added mass and damping, that is also we have discussed, right. So, using that you are getting this the diffraction force, that amplitude, and then you will get the Fruit-Kildler force amplitude. So, everything you can you can generate the right hand side is a harmonic motion, right, because you are getting this FD by this method, and plus you are getting the Fk by this method. So, therefore, you can generate your F exciting force is equal to this Fk into sin kx minus omega t, and then plus some Fd into again sin kx minus omega t. In that way you can get it. Okay. So, it is a very it is not very accurate, but what I wanted that you use this, and then at least you just write a code finally using the motion of the body. Okay, you have all the prerequisite, you know this how to solve this equation in time domain using Euler equation, you know how to get this in time domain, how to write the exciting force, you get the damping from this chart, it will be provided, and then you have to solve the equation of motion. So, that is actually your some kind of, you can say, the home assignment, and just for your try. Let us see how many of you can do this. Okay. Okay. Thank you very much.